Okay, YouTube, this is my first video in my module on measures of position of data. And up until now, we've considered measures of central tendency, that is where the center of the data is, that's like mean, median, mode, and mid-range. We've also talked about spread of data. So these statistics are things such as range, variance, and therefore also standard deviation. What we're going to do now is what we're going to assume is that we have a set of data, and we could say that it's this list of numbers here. We say x1, x2, x3, all of this data, all the way out to maybe the nth datum. And what we want to do is we want to describe where data lie within a data set if we were to assume that all of these were put in order from least to greatest, okay? It's just that this is sometimes hard to do. So in this first video, we're going to talk about a very simple measurement to calculate that we use all of the time, and we call this measurement a z-score, or a standard score, or a standard z-score. So as an example of why we use this as a measure of position, let's go ahead and consider this situation here, but it says sometimes I say it's very difficult to compare things that although they lie within maybe the same context, they don't share the same scale. Okay, so what we're going to do is we're going to take this example into consideration, but it says suppose you're a student and you score 90 on a math exam, but you score 45 on an English exam. The thing here is that these are both, of course, exams. It's just that when you compare how you did on the math exam to how you did on the English exam, they're really hard to compare to one another, and the reason why is because they're probably not out of the same amount of points. You know, this might have been a 90 out of 180, and this might have been 45 out of 46. So in terms of how you did, there's a high likelihood that these didn't have the same number of items, same scale. So what we're going to do in order to accommodate for these discrepancies, I call them, we're going to use a comparison of a relative standard here, okay? And so we say relative to what? Well, relative to the mean of the data set, and also relative to its standard deviation. Okay, so the middle of the data set and how it is on average spread from that middle. Okay, so if we put these into relation to the mean and standard deviation, we get what we call a standard score, or a z-score. And so I'm going to define what a z-score is here, and we're just going to run through how you calculate it twice, but I really want to understand what it is that we're talking about. So we say that a z-score, or a standard score for a specific data value. So up here in my data set, maybe I want to figure out the z-score for just one datum. We want to know where its position is, okay? We obtain this by subtracting the mean from the individual data value. So in this instance here, you can see that I say z equals, and I have value, so the actual x value minus the mean of the data set. And let's say I'm using a sample, I would say that this is x bar. So I would take this difference here, and then what we're going to do is we're going to divide that by the standard deviation of the set of data. Okay, so you can see that I have this x, which represents our datum, minus the mean of the data set. And we're going to divide that by the standard deviation, okay? And we use lowercase s for this. And you can see that I've written this down here twice. As a matter of fact, I should have written this vertically and not kind of horizontally oriented. But we say that for a sample, the z-score is z equals the datum minus the mean data value all over the standard deviation. And really what I want to write here is this. This top number here tells us the distance to the mean. In other words, given a datum, if you were to subtract off the average, what it's going to tell you is how far away from the average that thing was. So in order, to give you kind of a solid example here, let's say that there's an average score of an 85 on a quiz and you get a 90. When you take your data value, your datum, minus the mean, you get 5. So basically this is telling me that I'm 5 points, and notice that this was positive. It means that I was 5 points above average, okay? So when we divide this by the size of the standard deviation, what this is doing is it's converting it from, instead of being a number of pure raw distance units from the mean, it's telling us the number of these size things that we are from the mean, and these size things are, of course, the size of the standard deviation. So when we talk about the z-score for a data value, when I write this down here, I say the z-score really represents the number of standard deviation lengths that a data value x falls, and I say above or below the mean. And I do want to indicate this here. If z is positive, it's positive, okay, then the datum lies above average, or above the mean. Okay, because when we do this difference here, we take the data value minus the mean. It was bigger than the mean, so we're going to get a positive value. But I say also, if z is negative, okay, we say the datum, or that particular data value, lies below the average, or below the mean. And I want to consider this. What if we were to do this quotient here? We say take the datum minus the mean and divide by the size of the standard deviation. We would say, well, what if I got z equal to 0? What would be true about this data value if the datum minus the mean gives us 0? It would mean that the data value is the mean. Okay, so if z equals 0, then we say the datum is equal to the average, equal to the average or the mean. Okay, so we're going to run this calculation here, and you can see that I've written this for population as well. We say if it's a population, we're just using different symbols. Datum minus the mean is mu all over sigma, but these are the same measures, and they just tell us how many standard deviations you are above or below the mean for your particular data set. So let's consider this. A student scores a 65 on a prob-stats exam that had a mean of 50 and a standard deviation of 10. So what I'm going to do is this. I'm going to say prob-stats, and I'm going to write down a few bits of information here, like this. The data value that we have in question here is the fact that they scored a 65. And I've also said that for this data set, the mean is 50. So already what I can tell you is that this student has scored 15 points above average, which is what we're kind of looking at. But my real question is how many standard deviations above the average is this? And so what we have here is the fact that the standard deviation size is 10. Okay. We also say this, she scored a 30 on a pre-calc exam, so we're going to write pre-calc, and we say, okay, so her data value, this datum is 30, and we say this test had an average of 25. So also this student scored above average, so that's way cool, you know. In either instance, this person scored above average, but we say 5 points above average, but the standard deviation size was 5, okay. So the real question is, you know, compare the relative position on the two tests. In other words, what we're saying is this: which one did she do better on relative to the rest of the people in the data set, or relative to the mean and standard deviation? What we're going to have to do is not just find out how many points above average this person was, but also take into account the size of the standard deviation. So let's go ahead and do our z-score on this first data set here. We're going to take the datum, which is 65, minus the mean. That's easy to do. We're going to divide by the size of the standard deviation. In this case, we get 15 over 10. And without using a calculator, I should use a calculator, but I'm going to write 1.5, and I'm even going to write positive 1.5. Okay? So we should write this standard deviations. So in other words, on this first test, yes, they scored 15 points above average as a raw difference, but in terms of how many standard deviations above average they were 1.5 of these 10 unit length things above average, which is pretty good, I would say. So we say on the pre-calc exam, how did this person do relative to the mean and the standard deviation? Well, here's the difference here. The mean was 25, and the standard deviation size is 5, and they scored 30. So this means that it comes out to be 5 over 5, or 1.00 standard deviations. In other words, which test did they perform better on relative to the mean? We would say that they performed better on the prob-stats exam because they were more standard deviations above average than they were on this one over here. So let's take a look at this next example here. Let's say we have two tests, and this is how this student scored on these exams compared to these averages right here. This is, say, a different student. And then we have the standard deviation for each test here. We want to know on which test did they perform better on relative to the average and standard deviation. So we're going to calculate a z-score. So we say on test A, we say z equals x minus the mean all over the standard deviation, where we have the data value is 38 minus the average 40. So this is maybe not the ideal thing you'd want to have happen on your test, but this person scored 2 points below average. So the first thing I'll point out is you get -2 on top. And in the basement, we say, well, the standard deviation was 5, size 5. We are actually going to take the time to convert this to a decimal. And we say, okay, well, 2 being negative divided by 5 gives us -0.4. So we say -0.4 standard deviations. So they were, first of all, below average because it was a negative z-score, and they were about 4/10 of a standard deviation, or 2/5 of a standard deviation below average. So for test B here, we say that this student scored a 94 on this exam, and the average was 100. So in other words, we could say this right now, they scored 6 below average. That is the case. And so again, they scored below average. You know, that's okay, you have a bad day. But we say the size of the standard deviation, you know, this is comparing with everybody here. Taking into account their scores, the standard deviation size is 10. And so if we were to divide this by 10, and I can do this one without a calculator, we get -0.6 or -0.60, and this is number of standard deviations. So if I said, okay, well, which test did they do relatively better on? I would say they did relatively better on test A, which is interesting because I say they scored fewer standard deviations below average. And it'll depend upon, what you're considering here. If you're talking about blood pressure, you'd want to be below. But if you're talking about mile time, you'd want to be in the upper end. Maybe not a time. But weight, you'd want to be below the average and standard deviation if you're trying to lose weight. And that'd be a good thing. Whereas in this case, we want to be as least negative as possible. So the last thing I'll mention here is this. If you were to take an entire data set, all the data, if you were to transform all the data into z-scores, in other words, tell how many standard deviations they were above or below average, then I would say that the resulting distribution would have a mean of 0. That is to say, if you are the mean, then when you take your data minus the mean, you get 0. And also this, the standard deviation size would become 1. Okay. So we say a z-score then is actually just the number of standard deviations each value is from the mean for a given distribution, and that's how you calculate it. Cheers.